Welcome to a fascinating journey into the heart of what makes science, science. Today, we're diving into a core concept in the philosophy of science, falsifiability, a groundbreaking idea proposed by the eminent philosopher Karl Popper. Have you ever wondered what truly distinguishes a scientific theory from a mere belief or a pseudoscientific claim? What are the boundaries, the rules, that define legitimate scientific inquiry? Enter Karl Popper, an Austrian-born British philosopher who revolutionized our understanding of the scientific method in the 20th century. Popper challenged traditional views on how scientific knowledge progresses, introducing a criterion that would forever change how we evaluate scientific theories. Before Popper, many philosophers and scientists believed that scientific theories were proven by accumulating evidence that verified them. This approach is known as verifiability or confirmationism. This reliance on accumulated observations is rooted in inductive reasoning. You observe many white swans, so you conclude all swans are white. But as we'll see, this method has a fundamental flaw. No matter how many confirming instances you observe, you can never be absolutely certain that the next observation won't contradict your theory. The classic example is the black swan problem. You might see 1,000 white swans, but one black swan disproves the universal statement, all swans are white. Popper argued that instead of trying to asterisk verify theories, scientists should try to asterisk falsify them. This shift in perspective is crucial. Popper's core idea is that a scientific theory must be falsifiable. This means it must be possible, in principle, to conceive of an observation or experiment that could prove the theory false. If a theory cannot be proven false, then it isn't truly scientific. Scientific progress, according to Popper, comes not from confirming our beliefs, but from rigorously testing them, from trying our hardest to prove them wrong. If a theory withstands repeated attempts at falsification, it gains strength, but it's never proven true, only corroborated for the time being. Let's look at some examples to clarify this distinction between falsifiable and non-falsifiable statements. The statement, all swans are white, is falsifiable because you can imagine an observation that would prove it false, finding a single black swan. This makes it a scientific hypothesis. However, statements from astrology like your destiny is influenced by the stars or certain claims within psychoanalysis are often non-falsifiable. No matter what happens, an astrologer can always find a way to interpret events to fit their prediction, making it impossible to prove them wrong. This, for Popper, disqualifies them as scientific. So why is falsifiability so important for science? Firstly, it drives scientific progress. By constantly attempting to refute theories, scientists are forced to refine them, discard outdated ideas, and develop stronger, more accurate explanations of the world. It encourages critical thinking and intellectual honesty. Secondly, and perhaps most importantly, falsifiability acts as a demarcation criterion, helping us distinguish genuine science from pseudoscience. If a claim cannot, in principle, be disproven, then it lies outside the realm of empirical science. Karl Popper's concept of falsifiability remains a cornerstone of modern scientific methodology. It reminds us that the strength of a scientific theory lies not in its ability to be proven true, but in its openness to being proven false. This commitment to rigorous testing and critical self-correction is what truly defines the scientific endeavor.